Hello guys, and welcome back to a new lecture in the series of lectures on probability and statistics. So there are two main branches of statistics, including descriptive statistics and inferential statistics. We already learned that descriptive statistics summarizes and describes data through measures like mean, median, and standard deviation. And in this way, they provide a snapshot of data's characteristics. On the other hand, we have inferential statistics. In here, we use sample data to make predictions or generalizations about the population. And we can employ techniques like point estimation and hypothesis testing. Today, we're gonna learn about point estimation. Point estimation is a topic under inferential statistics. Point estimation involves using sample data to calculate a single value, or you can say a point estimate, and this value serves as an estimate of unknown population parameter. For example, the mean or proportion of a population. In today's session, we will explore foundational concepts, properties, and methods related to point estimation. Inferential statistics is very popular where we need inferring something based on some sample data, not whole data. We have no access to the population. There are many cases that we cannot collect data about all the members of a population. As you may hear several times, before elections, there are many estimations. In fact, they don't ask everyone about their vote, but they ask from a sample of whole population. So, inferential statistics is applied where there is no way or it's costly to collect data about all members of a population. Our learning objectives today are understanding what is the point estimate, exploring the statistical properties, discussing sampling distributions, and examining two estimation techniques like the method of moments and maximum likelihood estimation. Let's get started. Let's begin with parameters. To estimate a parameter, we first need to understand what it presents. In statistical inference, the term parameter is used to denote a quantity like theta, and that is a property of an unknown probability distribution. We don't know about this probability distribution. For example, mean, variance, or particular quantile of the probability distribution. Parameters are fixed numerical characteristics of a population, and parameters are unknown. So, one of the goals of inferential statistics is to estimate these parameters. So, once again, the ultimate goal of estimation is to infer these parameters based on observed data. This sets the stage for our discussion on estimation. Statistical inference is normally employed in order to draw some type of conclusion about one or more parameter, or you can say population characteristics. To do that, we need to gather sample data from each of our desired population. Then we can make some conclusion based on values obtained from various sample quantities. The objective of point estimation is to select a single number based on sample data that represents sensible value for theta. Theta is a generic symbol, and we use it for discussing general concepts and methods of inference. A point estimate is a single number we calculate from sample data to serve as a sensible guess for an unknown parameter. For example, we might use a statistic, it means computed from our sample, to estimate a parameter. So once again, a point estimate of parameter like theta is a single number that can be regarded as a sensible value of theta. It is obtained by selecting a suitable statistic and computing its value from the given sample data. So the selected statistic is called as point estimate of theta. We are dealing with population parameter, point estimator, and point estimate. The population parameter is a numerical characteristics of a population like mu, variance, proportion. Point estimator is a statistic. It means it's a function of the sample, and we use it to estimate the parameter. For example, sample mean, that we show it by x bar, for mu, that is for population. So this is for sample, this is for population. Then point estimate is the specific value of the estimator for a given sample. The process of point estimation is the foundation of making informed predictions from limited data. Here is a practical example. Imagine we want to find the mean height of all students in a class. So population is all student. The population is every student, and the population mean, we can show it by mu, is the average height of all of students. This mu is a population parameter, and this presents true mean height of students. In order to estimate mu, we may sample, like for example, you can say 10 students only randomly. From a sample, we calculate the sample mean, and we show this one as x bar, and this acts as our estimate of that population mean of mu. Then we measure their individual heights, and then we compute x bar, the average of our sample. Then the sample mean, like x bar, is an estimate of the population mean, which is mu. This is a classic case of point estimation in action. Now let's consider a real-world scenario. Automobile manufacturer has developed a new type of bumper which is supposed to absorb impacts with less damage than previous bumpers. The manufacturer has used this bumper in sequence of 25 controlled crashes against a wall and each 10 miles per hour using one of its compact car models. So in this case, we consider X as the number of crashes that result in no visible damage to the automobile. Our goal is to estimate P, which is the proportion of all such crashes that result in no damage. So if we observe X as 15, then estimator of P hat, we show P by P hat is equal to X divided by N. Then the most reasonable estimator and estimates are like P hat is equal to 15 divided by 25, which is equal to 0.6. It means we cannot test this bumper on all devices. We just run an experiment of 25 tests. This is a type of inferential statistics, and we conclude from some samples, and we conclude that for all population, we may get the same result. Moving on, let's define our terms more formally. The unknown parameter, like theta, that we are interested to estimate is not known. For example, you can say it can be mean, or it can be variance, or it can be standard deviation. It's a part of probability distribution, fx and theta, which describes how our data behaves. The parameter theta and the underlying probability distribution of fx and theta are the actual values that are unknown. We collect some data, these are the observations, so these parts are unknown to us, right? We collect some observation like x1, x2, x3 up to xn, these are the sample, and we use probability theory and a statistical model in order to compute a point estimate, and that is called as theta hat. So the observations are known to us, it means we can see them, we can check them. We use the probability as mathematical framework to model the relationship between the data and the unknown parameter through the probability distribution. The statistic is our best guess for the unknown theta. It means we guess theta hat for theta to be theta, but it's not always the same. We want to estimate a parameter of a population which we don't know. We select a sample of our population and we try to estimate the parameter. We guess it based on the sample data as a representative from the population. So the statistical reference is the process of using the sample data and probability theory to draw conclusions about the unknown parameter, and this results in point estimate. A good point estimator should have desirable statistical properties like unbiasedness, consistency, efficiency, sufficiency, and completeness. In the case of unbiasedness, an estimator like theta hat is unbiased if its expected value is equal to the true parameter, right? We can say that E of theta hat should be equal to theta. It means we guess the same. For example, the sample mean x bar is unbiased for the population mean like mu because E of x bar is equal to mu. However, the sample variance S2 is equal to 1 by n, sum of I is equal to 1 to n, xi minus x bar squared. This makes it unbiased. Later we will prove why. Then we have consistency. An estimator is consistent if it converts in probability to the true parameter as the sample size n increases. It means as n goes to infinity, theta hat should go close to theta. For example, the sample proportion like p hat is consistent for the population proportion because as larger samples make p hat closer to p. Then we have efficiency. Among unbiased estimators, the one with the smallest variance is most efficient, and these indicate greater precision. For example, for a normal distribution, the sample mean is more efficient than the sample median for estimating mu because it has lower variance. The next one is sufficiency. An estimator is sufficient if it captures all information about the parameter in the sample. A sufficient statistic uses the data efficiency without loss of information. For example, a Poisson distribution, the sample sum that we show by sum of xi, is a sufficient estimator for rate parameter like lambda. The last but not least, completeness. An estimator is complete if no function of it means other than a constant, is unbiased for zero across all possible parameter values. Completeness ensures the estimator is uniquely optimal. For example, for a normal distribution with known variance, the sample mean is a complete sufficient statistic for mu. Let's look at how population parameters relate to their sample estimate. For the population mean, we show it by mu. The empirical point equivalent is the sample mean that we show by x bar. And this x bar, I'll show you right here, x bar is equal to 1 by n sum of I 1 to n xi, right? This is the sample mean. For the population variance, we show it by sigma square, and in the case of sample variance, we show it by s square. And this one, this s square, is equal to 1 divided by n minus 1 sum of I from 1 to n xi minus x bar square. And we do the same thing for population standard deviation, sigma as the root square of sigma square, and in here we show by s as the root square of this s. And for the population proportion P, we use the sample proportion P hat is equal to what? X divided by n, where x is the number of sexes and n is the sample size. We should care that point estimators are never perfect. They always have an error component. We call this error component as margin of error. For example, we may say that we estimate that 30% of people of a country will vote for party A. And then we say plus minus 3%. It means when we say on average 30, right, it means our interval is from 27% up to 33%, right? Technically, this error is expressed as a confidence interval that we will study in the next lecture. The probability density function is unknown for the population. This function describes the distribution of our data, and since it is unknown, we rely on sample data to infer its shape and properties. In this graph, we have a population and there is a sample mean. So these are the data observations that are known for us, and this is the population mean, and this is the sample mean here. We try to come close to the population mean. It means we want to reduce this distance where we can have mu is equal to x bar. How we can make x bar close to mu hat? By taking more samples, but it's not exactly the same, right? So we tried a lot, but it's not exactly the same. As a simple example of a point estimate, we should care that an obvious point estimate of the mean mu of a probability distribution is the sample mean, like x bar, of data observation obtained from the probability distribution. In this case, the estimated value for the population mean is equal to the sample mean, so we can write mu hat is equal to x bar. This sets the stage for understanding how we estimate these distributions in practice. Now let's shift to statistics. These are quantities derived from a sample. The term statistics is used to denote a quantity that is a property of sample. For example, sample mean, sample variance, or particular sample quantile, these are statistics. These are random variables, and their observed values are calculated from our data. The sample mean and the sample variance are key examples we will explore further as we estimate population properties. Statistics are considered as random variables, and their observed value can be calculated from a set of observed data. So the sample mean is simply x1, x2 up to xn divided by the number, and the sample variance is sum of xi minus average divided by n minus 1. Estimation is all about guessing the properties of a population based on collected data. A point estimate, in particular, represents our best guess at the value of an unknown parameter. Since this estimate is statistic derived from the sample, it's a crucial tool in inferential statistics. Let's see how this works with some examples. So here we have an example with real data. So we have a data set, and here we have 15 observations, and these are the data that we have. So now we want to find the sample mean, sample variation, and sample standard deviation. So to do that, I'm going to use Excel. Excel is easy. Based on the equation that we had, we are interested in sample mean, we are interested in sample variance, and we are interested in sample standard deviation. So we know that x bar is equal to x1 plus x2 plus xn divided by n, and we know that the sample variance s squared is equal to sum of I from 1 to n xi minus x bar squared divided by n minus 1, and this one s is equal to root square of variance. So let's do it. So we have 1 to up to 15, and our values are 3193, 3124, 3153, 31. Okay, so first sum of all, right? Then average is equal to this one divided by this one, right? And also we can use average in Excel, average and you can select all together. You can see the same. For the variance, we need to do like this one minus average, right? And I'm gonna fix the average. So in this way, I can do average fix and square. All right, then sum of all together, and this one divided by n minus 1, right? This one divided by 15 minus 1, right? Sum this one. All right, for the standard deviation, simply SQRT of this one is 118, right? So we found that sample mean is equal to 3,210.73. Then the standard deviation is 13,832.5, and the standard deviation is 118, right? These statistics gives us a snapshot of the sample and they help us to estimate population parameters. But the question is, how close is the sample mean to the population mean? In order to increase the accuracy, we need to take more samples. So let's have more samples. It means we repeat sampling, right? In the first sample, we found that mean is 3,210. Then we did again 15 sample, we calculated mean again. So we repeated the sample and we calculated the mean for each sample. So we come up with this table. Now, the question is, what is the distribution of these sample means? In this table, you can see here, this is the range, right? We calculated range from 2,950 to 3,049. This is a range, and we count the frequency. It means how many mean we have in this portion, right? So in total, we have 9, right? 1, 2, 3, 7, 8, 9, right? So it means among these means that we have, one of them is in this interval. 1 is in this interval, 4 is in this interval, 2 in this interval, and 1 is in this interval. So this one is the frequency, means how many sample means we have in this range. We normally call this table as sampling distribution. So our goal is to estimate the population mean. So the expected value of sample distribution should be equal to the population mean. We write Ex bar is equal to mu. If we take many random samples from the population, each with its own sample mean, and then we create a distribution based on all those sample means, then the mean of that sampling distribution is equal to the mean of the population. In general, bias means prejudice in favor of one or against something. In our measurement devices, we may have wanted or unwanted errors. So we defined unbiased estimator. An unbiased estimator is one where expected value of the estimator is equal to the true parameter. So we write that unbiased estimator E theta hat is equal to theta for all theta. Then we call it as unbiased. Otherwise, we call it as biased. The theta hat is unbiased if its probability distribution is always centered at the true value of the parameter. The bias of an estimator is defined as the expected value of the estimator minus the parameter. So if this is 0 for any unbiased estimator, if this value is equal to 0 for any unbiased estimator, it means our estimate on average hits the true value. For example, we have like theta hat as unbiased estimator. Then if theta is equal to 100, it means the sampling distribution should be centering at 100. And for example, if you have theta is 27.5, then the theta hat sampling distribution is centered at 27.5. So you can see here we have different distribution. This is the probability density function for theta hat 1, and this is the probability distribution for theta hat 2. And this one is the bias of theta hat 1, right? The distance. And again, here we have the bias of theta hat 1. Here is an example to check our unbiasedness. Suppose we have an estimator and we wanna see if it is unbiased estimator of a parameter or not. The bias will be calculated as the expected value of the estimator minus the parameter, as we have seen already. So E of theta hat should be equal to theta. So we want to check whether mu hat is equal to x plus y is an unbiased estimate of mu or not. So E of mu hat is equal to E of x plus y, and this one is equal to E of x plus E of y, right? Then we have already E of x as mu2 and E of y as mu, right? So we write this one as mu2 plus mu, which is equal to 1.5 mu. So we want to calculate the bias. So the bias is E of mu hat minus mu should be equal to 0, right? If it is unbiased. So E of mu hat minus mu should be equal to 0 if it is unbiased. So we already found that this one is 1.5 mu. minus mu is equal to 0.5 mu, and it's not equal to mu. So we found that this is not equal to mu and it is biased. For a success probability, if you have a sample where some trials succeed, then the sample proportion can serve as an unbiased point estimate of the population success probability, or you can say P. So here we have a random variable x, which follows a binomial distribution with n and p. In the binomial distribution, we have x as the number of successes that we'll achieve in n independent Bernoulli trials, and each is either 0 or 1, and this is the probability of success that we show by p, right? So we want to go for point estimate of success probability, and our x follows the binomial of n and p. Then p hat is equal to x by n, and the expected of x is equal to n multiply p. Then e of p hat is equal to e, right? And this one will come here, x by n is equal to 1 by n ex is equal to 1 by n np is equal to p. It means p hat is an unbiased estimate. Suppose we have a random sample of x1, x2 up to xn, show that the sample mean is an unbiased estimator of theta is equal to exi. Our sample mean theta hat is equal to x bar is equal to x1 plus x2 plus x3 plus up to xn divided by n. So we have the bias of the estimator, right? We can write this one, for example, b theta hat as the bias of the estimator is equal to e of theta hat minus theta. This should be equal to 0. If it's equal to 0, it's unbiased, right? So this e of theta hat, we can write e of x bar minus theta, and this one is equal to e of xi minus theta, which is equal to 0, right? In here, this e theta hat is the expected value of the estimator, and theta is the true population parameter being estimated. And we believe that an estimator is unbiased if it is equal to 0, so we find it here as 0. When estimating the population mean, if we take a sample observation from a distributed with mean as mu, then the sample mean, like mu hat, which is equal to x bar, is an unbiased point estimate of population mean mu. So for this one, we consider sample observation that has been sampled from a population, right? It means what we have estimated is exactly the same as the actual mean of the population. Because exi is equal to mu and I is between 1 to n, then e of mu hat is equal to e of x bar, and this one based on the equation is 1 by n e of sum of xi. This equals to 1 by n sum of xi, and the sum of exi is in mu, which is equal to mu. So you can see from the equation that we do the expectation for all the sample, and finally we try to conclude the population mean. In the same way, for the population variance, if we sample from a distribution with variance like sigma squared, this is the sample variance, and s squared, that is an unbiased point estimate of the population variance. So if we have like x1 and up to xn as the sample observation from a probability distribution with variance of sigma squared, then the sample variance, that sigma hat squared, is equal to s squared, which is equal to sum of x minus x bar average divided by n minus 1. This is unbiased point estimate for the population variance of sigma squared. This ensures our variance estimate is reliable across repeated samples. Minimum variance estimates are statistical estimators that achieve the lowest possible variance among all unbiased estimator of a parameter. This shows the probability density function of two estimated parameters. This is probability density a function of theta hat 2, and this is for theta hat 1. Theta hat 1 and theta hat 2 have symmetric distribution because both of them, they are symmetric. Both half is the same, right? Also, suppose that distribution are both centered as theta that you can see here, so that they are both unbiased point estimate of theta. We wanna compare them and find out which one is better. It seems they are different in terms of variance. In this figure, we can see that theta hat 2 is a better point estimate compared to theta hat 1, because variance theta hat 1 is greater than variance theta hat 2. The theta hat 2 is a better point estimate because the variance of theta hat 1 is greater than variance of theta hat 2. Since the unbiased point estimate of theta hat 2 is better than unbiased point estimate of theta hat 1 because it has a smaller variance, right? So we can write that probability of theta hat 1 minus theta is less than sigma, and this one is less than probability of theta hat 2 minus theta less than sigma. So far, we understood that the best possible condition to make point estimate is being unbiased and it has smallest possible variance. Minimum variance unbiased estimate, this is an unbiased point estimate whose variance is smaller than any other unbiased point estimate. Such kind of estimations are clearly good ones. The efficiency of an unbiased point estimate is calculated as a ratio of the variance of the point estimate and the variance of minimum variance unbiased estimate. In this sense, the minimum variance unbiased estimate can be described as the most efficient point estimate. Then we have relatively efficiency. This is relatively efficiency of an unbiased point estimate like theta 1 to unbiased point theta 2 is variance of theta hat 2 divided by variance theta hat 1. So the next topic is mean square error or MSE. This is another important metric. MSE or mean square error is used as a metric to find the amount of error in a statistical model. MSE measures the average square difference between the estimated and true parameter values, and in this way they can combine bias and variance. In some conditions, it may be useful to compare two-point estimates that have different expectations and different variance. In such cases, it is usual to prefer the point estimate that minimizes the value of MSE. So we find MSE as MSE of theta hat is equal to expectation of theta hat minus theta square, right? And this one is equal to expectation of theta hat minus expectation of theta hat plus this one plus expectation of theta hat minus theta and all square, right? This one we can rewrite as expectation of theta hat minus expectation of theta hat square plus 2 times of E of theta hat minus theta into expectation of theta hat minus expectation of theta plus expectation of theta hat minus theta square. And this one we can rewrite as expectation of theta hat minus expectation of theta hat square plus expectation of theta hat minus theta square. And this is variance. Based on the definition, this is the variance and this is the bias, right? So we can say that these are variance of theta hat plus bias square. This is the expectation of the square deviation of the point estimate about the value of the parameter of interest. For the sample proportion, if we have a number of success in trials, the sample proportion is an unbiased estimate of success probability. Now, we want to study more about probability distribution or sampling distribution of the sample proportion like we had, and the sample mean X bar and the sample variance. If you have a random variable and this random variable follows binomial distribution of n and p, then the unbiased estimate of success probability p is p hat x by n. This is known as the sample proportion because it represents the proportion of success observed in a sample of n trials. This has an approximation distribution as you can see here. The p hat follows a normal distribution with p and p multiply 1 minus p, probability of success, probability of failure divided by n. The standard error of p hat, which is root square of p multiply 1 minus p divided by n. The standard error provides an indication of the accuracy of the point estimate of p hat. It means if we have smaller values of standard error, it means the point estimate is likely to be more accurate. Expectation of p hat is equal to p, and variance of x is in p multiplies probability of failure. Variance of p hat is equal to variance of x by n, which is equal to p multiply 1 minus p divided by n. The distribution of the sample mean is governed by the central limit theorem. If we have observation from a population with mean mu and variance sigma square, then the sample mean approximately follows a normal distribution as the sample size increases, which is really considered as a powerful result for inference. So it means if we increase the number of samples, then we can finally come up with a normal distribution. This is central limit theorem. The standard error of the sample mean is sigma over the square root of n. Since sigma is often unknown, we use s over the square root of n instead for standard error. This metric tells us how much the sample mean varies from the population means. It can help us for confidence in estimation. So here is an interesting question. If you use a certain sample size, what is the probability that the sample mean lies within a certain distance of the true mean? This depends on the standard error and the distribution, which we will explore next with an example. So if a sample size n is equal to 20 is used, what is the probability that the value mu hat is equal to x bar lies within the mu 4 of the true mean mu, right? So it means what is the probability of x bar between mu minus 4 sigma by 4 mu plus sigma by 4, right? And because our random variable follows a normal distribution of mu and sigma 2, then we can say that the x bar follows a normal distribution of mu and sigma 2 divided by n, which is equal to n mu and sigma 2 divided by 20, because n is equal to 20. Then here, the standard deviation of x, we can write the standard deviation of x is equal to root square of sigma 2 divided by 20, which is equal to sigma divided by root square of 20. Now, we can go for standardization. So this one is equal to probability of x bar minus mu divided by sigma by root square of 20 between mu minus sigma by 4 minus mu divided by standard deviation, right? Sigma divided by root square of 20, and the same here, mu plus sigma divided by 4 minus mu divided by sigma root square of 20. So we need to compute the bounds. Minus sigma divided by 4 divided by sigma divided by root square of 20. This one is equal to minus sigma divided by 4 multiply root square 20 divided by sigma, which is equal to root square of 20 divided by 4. And in the same way, we can do sigma divided by 4, sigma divided by root square of 20 is equal to 20 by 4, right? Minus plus. What is the value for root square of 20? Approximately 4.472. And this one divided by 4 is equal to 1.118. And we can rewrite this one as approximately 1.12, right? We can say that we use this z. This is approximation of this 1.118, right? So we can rewrite this one as probability of z between 1, 1, 2 minus 1, 1, 2, okay? And this one is equal to phi of 1, 1, 2 minus phi of minus 1, 1, 2. Based on the table that we had, z table, this is equal to 0.8686, right? 1.2. So this will be 0.8686 minus, and for this one, we should go for 1 minus this one, right? So it will be 1314, which is equal to 0.7372. So 74% is the probability that the value of the mu hat equal to x bar lies within the sigma 4 of the true mean. Point estimators can be calculated using various methods depending on the nature of the parameters being estimated and also the characteristics of the sample data. Point estimation methods are used to provide a single best guess, or you can say point estimate of an unknown population parameter based on sample data. The primary methods here are methods of momentums, maximum likelihood estimation, least square estimation, Bayesian estimation, and median or quantile estimation. Method of moments estimates parameters by equating sample moments with corresponding population moments like mean, variance, etc. This method of moments is simple and intuitive, but not always efficient. The next one is maximum likelihood estimation. This estimates parameters by maximizing the likelihood function. It means the probability of observing the given sample. This maximum likelihood estimation is asymptotically efficient and it is widely used due to desirable statistical properties. The LSE, least square estimation, this is normally common in regression, and this minimizes the sum of square difference between the observed and predicted values. The Bayesian estimation combines prior distribution with the likelihood using Bayes' theorem in order to obtain the posterior distribution. And the last but not least, the median or quantile estimations is especially useful in robust statistics, and this minimizes the sum of absolute deviations like median or target specific quantiles. Each method has its theoretical assumption, and each one is suitable depending on the data characteristics, underlying distribution, and computational considerations. So we are going to study the method of moment. So far, we studied the obvious point estimate for success probability, the population mean, and the population variance. It is often of interest to estimate parameters that require less obvious point estimate. In the case of method of moments, we estimate a parameter by equating sample moments to their population moments. For a data set with one known parameter, this method provides a point estimate based on the observed data. So the method of moment is a point estimate for one parameter. In this method, the estimator is chosen to match the sample moments, like mean and variance, with the corresponding population moments. If a data set consists of observation x1 to xn for a probability distribution that depends upon one known parameter like theta, then the method of point estimate theta hat is x bar is equal to e of x and sigma squared is equal to variance of x. right? So these are the sample parameters, these are the population parameters. In other words, the point estimate is found by setting the sample mean equal to the population mean. Normally distributed data provide a simple example of estimating two parameters by the method of moments. So for a normally distributed data, since Ex is equal to mu and variance of x is equal to sigma square, the method of moments gives x bar is equal to mu hat and s square is equal to sigma square, which is equal to 1 by n sum of I from 1 to n xi minus x bar squared. You see that this method of moments is not that much complicated. We can simply find out sensible point parameters. Therefore, this is straightforward and yields sensible estimates because the sample mean and variance are intuitive estimators for the normal distribution parameters. However, let's see the case of method of moments for a uniform distribution. So we have uniform distribution u of 0 and theta. It's a uniform distribution and it means the data values x are uniformly distributed between 0 and theta. The upper endpoint of the uniform distribution is the unknown parameter, and we want to estimate that parameter. So you can see we have a data set like 2, 2.4, 3.1, 3.9, 4.9, 4.8, 5.7, and 9.9. We find the average, right? The average of the sample is equal to sum of all divided by number, right? 1, 2, 3, 4, 5, 6, 7, 8. Then we can find it at 4.5375. Sum of them together divided by 8. We know that the expectation of uniform distribution of u0 and theta is Ex theta divided by 2, right? Then our theta hat is equal to 2 multiply this one, 2 multiply 4.5375, which is equal to 9.075, right? This is a big problem here because one of the data observation 9.9 is greater than this one. Is greater than theta hat. So there the true value of theta must be larger than the all data values, right? Because theta is the maximum value, but in here theta becomes less than one of the values. Theta must be at least as large as the maximum observed value, not less than this one. Because all data point must lie between 0 and theta. The method of moments does not work here. Although the method of moments did not work in this example, however, for the other example, it can be used. For this uniform of 0 and theta, a better estimate for theta hat would be the maximum observation. Like, for example, we can write as theta hat is equal to max of xi, which is equal to 9.9, as it ensures all data points lies between the range of 0 and theta hat. Another approach is maximum likelihood estimation, or MLE in short. MLE is a technical method for obtaining point estimates. For one parameter, we use observations and their probability distribution in order to find the value of the parameter that maximizes the likelihood function. This estimate, like theta hat, is our best fit based on the data. Maximum likelihood estimation involves finding the parameter value that maximizes the likelihood function, and this measures the probability of observing the sample data give different values of the parameter. In MLE method, the parameter values are found such that they maximize the likelihood that the process described by the model produced the data that were actually observed. For the MLE for one parameter, if the data observation are from x1 to xn from the probability distribution of f, x, and theta depending upon one unknown parameter of theta, then the MLE theta hat of the parameter is found by the maximizing the likelihood function. This is called as likelihood function is equal to fx1 theta multiply up to fxn theta. So in the case of Bernoulli distribution, we have two outcomes, yes or no, 0 or 1. The random variable can be 1 with the probability of p, and it can be 0 with the probability of 1 minus p, right? So if we have x1 to xn as a set of Bernoulli observation, in this case, the probability distribution, like PMF, is for 1 and p is p, and for 0 and p is 1 minus p. Or we can write probability of f, xi, and p is equal to probability of p in power of xi multiply 1 minus p, 1 minus xi. And in this case, the likelihood function of lx1 and p is equal to product of 1 to n pxi 1 minus p, probability of success, probability of failure 1 minus xi, and this equals to p in power of x 1 minus p n minus x. For two parameters, if a data set depends on two unknowns, we maximize the likelihood function to estimate both parameters at the same time. This process extends the single parameter case, requiring more complex optimization. So if a data set consists of observation x from x1 to xn from a probability distribution of f, x, and theta1 and theta2 depending upon two unknown parameters, then the maximum likelihood estimate of theta1 and theta2 can be written as likelihood of x1 and theta1 theta2 is equal to f x1 theta1 theta2 multiply up to xn theta1 theta2. Here, one example, we want to find the likelihood function if x follows a binomial of 3 and theta, and we have observation of like x1, x2, x3, x4 is equal to 1, 3, 2, 2, right? We already learned that when we have random sample like xi, and this is iid, so we can find the joint PMF or joint PDF by multiplying the marginal PDF or PMF. So if x follows a binomial of 3 and theta, then the probability mass function of a single observation xi, we can write as probability of xi, x and theta is equal to 3 and x, combination of 3 and x, then theta in power of x, 1 minus theta in power of 3 minus x, right? Success probability, failure probability. Because the sample are iid, then the joint PMF is the product of joint marginal. So we can write likelihood of x1, x2, x3, and x4, and theta is equal to probability of x1, x2, x3, x4, x1, x2, x3, and x4, and theta is equals to probability of x1 and theta multiply probability of x2 and theta multiply probability of x3 and theta multiply probability of x4 and theta, right? And this one, this equals to 3 combination of 3 and 1 for the first one, for the second one 3 and 3, for the third one 3 and 2, for the fourth one 3 and 2, multiply theta in power of x1 plus x2 plus x3 plus x4, multiply 1 minus theta, and n sum is equal to 12 minus x1 plus x2 plus x3 plus x4. Since we have observed already x1, x2, x3, x4 as these values, then we can write L likelihood of 1, 3, 2, and 2 is equal to 3, 1, 3, 3, 3, 2, 3, 2, theta in power of sum of them 8, multiply 1 minus theta, 12 minus 8, 4, right? So combination of these 3 and 1 is equal to 3, 3 and 3 is equal to 1, and so the sum of these all will be 27, and this will be equal to 27 multiply theta in power of 8, 1 minus theta in power of 4. Okay, so let's go back to our example. An automobile manufacturer has developed a new type of bumper which is supposed to absorb impacts with less damage than previous bumpers. The manufacturer has used this bumper in a sequence of 25 controlled crashes against a wall, and each with 10 miles per hour, using one of its compact car models. Now, our random variable x is the number of crashes that result in no visible damage to the automobile. Suppose x is observed to be 15, right? So our sample size n, so sample size or n is equal to 25 crashes that we have here. So the number of successes is k equal to 15. It means crashes with no visible damage. And then we have a parameter theta. This is the true proportion of no damage crashes. So this what we have here is sample, not population, right? We want to estimate this one. The observed proportion, so this is the true proportion, but the observed one, so I can write here like theta hat is equal to 15 divided by 25 is equal to 0.6. This is the observed proportion. Our goal is to estimate the true proportion. So we have defined that a point estimate is a single number used to estimate an unknown population parameter, that is theta here, the true proportion of our population, right? We did this estimation by the observed proportion, and we found that 0.6, right? It means the point estimate is theta hat 15 by 25.6, it means 60%, right? Next, we're gonna for sample proportion. So suppose we have k, and this k follows a binomial of n and theta, right? So theta we already found here. Theta is equal to theta hat is equal to k divided by n, and the expectation of theta hat is already we found as theta. And then variance of theta hat is equal to theta 1 minus theta divided by n, right? So if we have a large n, if n is too large, right, too many based on the CLT, central limit theorem, if you have too many samples, right, then theta will follow, approximately follows n of theta, and theta multiply 1 minus theta divided by n according to the central limit theorem. Then we can define the standard error of theta is equal to root square of variance, right? Root square of theta multiply 1 minus theta divided by n, right? We can now find the standard error. So this one is equal to root square of 0.6 multiply 1 minus 0.6 is 0.4 divided by n is 25, and this one is approximately 0.098. So it means our theta hat approximately follows a normal distribution with 0.6 and 0.098 square, right? So we can conclude that the estimator of this theta hat k by n for a binomial distribution with theta hat is equal to 0.6 and sample size of 25 is approximately normally distributed with mean of 0.6 and a standard deviation of 0.098 and a standard error of 0.098. Okay, let me clean this one. Now we're gonna find the probability that theta hat lies within plus minus sigma divided by 4 is approximately plus 0.01, right? It means we already found that this sigma is equal to 0.098, right? But if we divide by 4, it will be not easy to calculate, so we just add 0.05. It means we want to have an approximation or rounding for simplicity. So we already found that theta hat is equal to 0.6. Now we're going to try this interval, 0.5 and 0.7, right? This one minus 0.1 and 0.6 plus 0.1, right? Next, we need to standardize the estimator theta hat by measuring how many standard errors it deviates from the estimated mean, that is 0.6 here, right? Z is equal to theta hat minus theta divided by standard error of theta hat. This approximately is equal to theta hat minus 0.6 divided by 0.098. Now we're gonna find theta hat in two cases, if theta hat is equal to 0.5 and if theta hat is equal to 0.7. If theta hat is 0.5, then it will be 0.5 minus 0.6 divided by 0.098, which is equal to minus 1.2. And this one is equal to 0.7 minus 0.6 divided by 0.098, which is equal to 1.02. So we found minus 102 plus 102. The probability that z, this our z, lies between minus 102 and plus 102 is equal to, approximately equal to phi of 1.02 minus phi of minus 102, which is equal to, how to find phi of 102 based on the table that we have. So 1 is here and 02 is here. So the result is 0.8461. So this one is 0.8461. This one is 1 minus this value, right? So it will be 0.1539. All right. And the result is 0.6922. So repeat the probability of 69.2%, it lies in this interval. Next, I want to try the method of moments and maximum likelihood for this problem. For the method of moments, we equate the proportion moment, that is Ex is equal to theta, to sample moment that we found, theta hat is equal to k divided by n. So very easy. Theta is equal to 15 divided by 25 is 0.6. And we said theta is equal to theta hat is equal to 0.6. That's all, right? So this is the method of moment. Next, I'm gonna try the maximum likelihood, or MLE. So we wanna utilize MLE process for estimating the proportion of theta in a binomial distribution based on n is equal to 25 and k or x is equal to 15. We have a likelihood function based on the equation that we already had, combination of n and k, theta in power of k, and 1 minus theta in power of n minus k. This function gives the probability of observing k success. It means no visible damage in n trials. And we know that theta is the true proportion of success. So in order to find the best estimate of theta, we need to maximize this one, right? So to simplify this one, we take log likelihood, right? It means ln of L theta is equal to ln of nk, combination of n and k, plus k ln theta plus n minus k ln 1 minus theta. Because this ln combination of n and k is constant, so it does not affect the maximum. Then we compute the derivative with respect to theta and we set it 0 to find the critical point, right? So we can write the derivative of this all with respect to d theta. So the derivative of ln L theta is equal to k by theta minus n minus k divided by 1 minus theta, and we set it as 0, right? So this one, we can write it as k divided by theta is equal to n minus k divided by 1 minus theta, right? So if we do cross multiplication here, we come up with k 1 minus theta is equal to n minus k into theta, right? Then in here, k is equal to n theta, then theta is equal to k divided by n, right? And what is our k? Is 15 divided by 25 is 0.6, right? In here also we found that theta hat is equal to 0.6. The estimated proportion of crashes with no visible damage is like 60%. Now let's move to the Python coding. All right, so for coding here, we need to import numpy as np. We need to import matplotlib.py plot as plt. Okay, so here we define our parameter n is equal to 25 and k is equal to 15, right? So we have theta underscore hat for moment is equal to k divided by n, and the theta hat for MLE is equal to, again, k divided by n, right? So this is MLE estimator. This is exactly same as the method of moments. Then we can print them, right? For example, print f. So both of them are same and 0.6. Then we're gonna plot them using a bar chart of point estimate. So plt.figure and fig size is equal to like 6 and 4. Then here we labels equals to MOM estimate and MLE estimate. Then estimate is equal to 2 that we have defined here, right? Now, bar plot of labels and estimates. In here, because both are the same. So PLT title, and let's see this one. So this is the MOM estimate and MLE estimate. Both are the same. Then we can go for visualizing sampling distribution. So np random.seed of 42. Then in here, simulated proportion. This is equal to np.random, and our distribution is binomial, right? Binomial of n theta hat MLE and 1000 divided by n, right? So we did it. Now we can go for plotting. So plt dot figure size 10 and 6, then plt histogram. Simulated proportion being 30, density is equal to, so here we should have density is equal to 2, alpha is, and color is equal to blue, and that's all. So here it is. Next, we're gonna add it some lines to show the estimation. So the same here, you can see here we have 0.6 added here. So this plot shows some simulation with like 10,000 samples, and then we find the proportion, then we plot it, and also we show this estimate here. So we can add PLT legend here as well. So you can see this blue color is for simulated proportion, but MLE estimate and MOM estimate both are the same, so you cannot see the red one. Okay, that's all. And so what are the limitations of this point estimation? Point estimations has some problem like uncertainty, outlier problem, assumptions, and sample size. Point estimation lack measure of precision, and that's why we use confidence interval or posterior distribution in order to solve this uncertainty. Then the estimators like X bar are sensitive to extreme values, which are called as outliers. MLE method assumes a specific distribution, so this is also may not work everywhere. The last one is large samples improve accuracy and consistency. So it means with lower sample size, the output will not be as wanted. Okay, in conclusion, point estimation is a critical statistical tool for estimating population parameters. So understanding properties like unbiasedness, consistency, efficiency, sufficiency, and completeness ensures the selection of robust estimators. In this lecture, we have covered point estimates, their properties, sampling distribution, and construction methods like MLE and method of moments. Thank you for watching and see you in the next lecture.